Alright, so here we have a 1342 nanometer infrared wavelength laser, and it's operating at around 100 milliwatts. So since this light is infrared, we're actually unable to see it. If we use a paper, we can't see the beam coming out at all. So it's invisible to the naked eye. However, we have an infrared viewing card. This card has photosensitive liquid crystals that enable you to see this light by re-emitting light at a visible wavelength. So you can see a red light there from the infrared. So we also have a piece of silicon wafer. This wafer is polished on both sides of it, so it's reflective on both sides, and to us it looks opaque. We can't actually see any light transmitting through it. So there's no surface roughness, there's no light scattering, it's nice and smooth. So we can't see any light going through it. However, we know that from class that silicon has a band gap of around 1.12 electron volts, and so we can use the Planck-Einstein relation to find that this 1.12 electron volts has a wavelength of about 1,100 nanometers. This means that silicon is capable of absorbing all wavelengths below that. You can see here in the visible region it has a very low transmittance because it's absorbing, but above that 1,100 nanometers wavelength, there is about 50% transmission. So this means that with our laser wavelength of around 1,342 nanometers, we should be able to transmit that light through the silicon wafer and view it with the IR card. So now we'll try that. So here's a piece of silicon. Just a moment. So we have a piece of silicon. We have our IR viewer card. We can see the beam with the card, and if we place the silicon in front of the laser like that, we can still see that beam. So that's pretty good. Now if we try the same thing with something like a piece of paper, we'll notice that we can see the beam with the card. If we use a piece of paper in front of the beam, we're unable to see that beam at all. So that means to us that the paper is not transparent to the IR, but the silicon wafer is.